Welcome to this deep dive into advanced retrieval augmented generation, or RAG systems. In this video, we'll explore the most critical architectural challenges, solutions, and real-world applications that define state-of-the-art RAG pipelines. Whether you're building intelligent assistants, search engines, or enterprise knowledge tools, understanding these advanced concepts will help you design robust, scalable, and accurate systems. Let's start by unpacking the core limitations that drive innovation in RAG architectures. One of the most notorious limitations in large language models is the lost-in-the-middle phenomenon. This occurs when models can easily extract information from the beginning and end of a long prompt, but struggle to recall details buried in the middle. This structural issue can lead to critical facts being overlooked, especially in lengthy documents or complex queries. Understanding this limitation is essential for anyone designing advanced RAG pipeline. Overcome the lost-in-the-middle issue. Advanced RAG pipelines use a multi-stage retrieval and reranking process. First, the system retrieves a broad set of documents, such as the top 30 results. Then a cross-encoder reranker isolates the 5 most relevant chunks. These high-signal chunks are strategically reordered, so that the most important information appears at the very top and bottom of the final prompt. This ensures that critical details are not missed by the model. Imagine a financial assistant tasked with extracting revenue numbers from a long prompt containing 20 text chunks. Without reranking, the model might miss key data. By filtering out noisy chunks and placing the most relevant information at the start of the context block, the assistant ensures that critical revenue figures are always surfaced and accurately processed. This approach prevents important details from being lost in the shuffle. A reranker acts as a sophisticated second-stage filter in the RAG pipeline. After the initial vector search retrieves candidate documents using fast, independent vector math, the reranker, often a cross-encoder model, analyzes the full sentence interactions between the query and each chunk. This deep contextual alignment allows the system to re-rank results based on true relevance, not just keyword similarity, ensuring that only the most contextually appropriate information is passed to the LLM. Consider a user searching for "how do I cancel my plan?" The initial vector search might return a chunk about canceling shipped orders due to keyword overlap. However, the reranker evaluates the actual context, recognizes the mismatch, and lowers its rank in favor of a chunk that directly addresses account cancellation. This ensures the user receives the most accurate and relevant information, improving both precision and user satisfaction. Hybrid search combines dense vector search for semantic meaning with sparse keyword search for exact matches. These two approaches run in parallel, each producing a ranked list of results. However, because their scoring systems are fundamentally different, simply adding their scores isn't possible. This is where Reciprocal Rank Fusion, or RRF, comes into play, merging the strengths of both methods. RRF solves the challenge of merging disparate scoring systems by focusing on the positional rank of each item across both result lists. Instead of relying on raw scores, RRF calculates a combined score based on how highly each document ranks in the dense and sparse lists. This ensures that items highly ranked by either method are surfaced at the top, providing a balanced and effective retrieval strategy. For example, searching for iPhone 15 Pro Max case with hybrid search means the dense vector locates protective accessories, while the sparse keyword search locks onto the exact product tokens. RRF then merges both lists, ensuring that the most relevant and precisely matching case appears at the top. This approach maximizes both coverage and accuracy in product search scenarios. Evaluating RAG systems without human annotators is made possible by the RAG triad framework. This approach uses an LLM as a judge to measure 3 core relationships: context relevance, groundedness or faithfulness, and answer relevance. By automating these checks, the framework can flag issues like retrieval noise, hallucinations, or incomplete answers, ensuring high-quality outputs without manual review. Suppose an AI assistant generates a brilliant answer that isn't supported by any retrieved text. The RAG triad framework automatically flags this as a groundedness violation, indicating the model hallucinated the answer from its pre-trained weights. This automated process helps maintain trust and reliability in AI-generated responses, especially in critical applications. August is an open-source evaluation framework designed to quantify RAG pipeline performance using metrics like context recall, context precision, and faithfulness. It generates synthetic testing datasets by ingesting raw company documents and using an LLM to create complex, multi-hop questions, target answers, and grounding contexts. This enables large-scale, automated testing without manual effort. Instead of hearing humans to write hundreds of test questions, Raga scans internal documentation and automatically generates high-quality test queries and validation parameters overnight. This dramatically accelerates the evaluation process and ensures comprehensive coverage across all knowledge domains, making it easier to maintain and improve RAG pipelines. Handling multi-hop analytical queries requires breaking down complex questions into simpler subqueries. Query decomposition uses an upstream LLM step to analyze the user's question, split it into distinct parts, and execute independent retrieval passes for each. The results are then consolidated and delivered to the final LLM prompt, enabling accurate and comprehensive answers. For example, if a user asks, "Did company A make more revenue in 2023 than company B?" the system splits this into 2 queries, one for company A's 2023 revenue and one for company B's. It retrieves the relevant data for each, then feeds both to the LLM for comparison. This modular approach ensures that even complex, multi-part questions are handled with precision. IDO is a powerful retrieval technique where an LLM first generates a hypothetical or placeholder answer to a user's query, even if it contains fabricated facts. This hypothetical text is then embedded and used to search the vector database, matching answer to answer rather than question to answer. This approach captures the semantic patterns of a proper response, improving retrieval accuracy. Pose a user queries, error 502 with Nginx on AWS Cloud. A direct question search might only return general documentation. With HIDA, the system generates a fake troubleshooting response containing typical logs and error steps. Searching with this hypothetical answer surfaces actual internal runbooks with similar log configurations, leading to more precise and actionable results. Robust state management is crucial for multi-turn conversational RAG. The query condensation pattern takes the entire chat history and the latest user input, then uses a lightweight LLM step to rephrase the conversation into a standalone explicit search query. This process strips out pronouns and ambiguous references, ensuring accurate vector database matching every time. For instance, if a user first asks about the Tesla Model 3 and then follows up with, "How much does it cost?" the system condenses this into current purchase price of the Tesla Model 3. This ensures the search query is clear, explicit, and contains all necessary references, leading to more accurate and relevant results from the vector database. Context separator tags are structured identifiers, such as XML tags or simple markers, used to isolate source data injections within an LLM prompt. These tags clearly demarcate where the source text begins and ends, preventing the model from confusing raw context with system instructions. This simple technique guards against context bleeding and accidental prompt misinterpretation. Without separator tags, a retrieved document might contain instructions like "please rewrite the above guide," which the LLM could mistakenly execute as a command. By wrapping source data in tags like docID equals 1, the system makes it clear where the context starts and ends, ensuring the model only processes the intended information. Extracting structured data from PDFs is a major challenge. Standard text parsers often flat multi-column tables into unreadable strings. Advanced RAG pipelines use layout-aware or vision-based PDF extractors such as LlamaParse to convert tables into clean Markdown or HTML. Alternatively, LLMs can summarize tables for retrieval, but inject the raw table into the final prompt for accuracy. Consider a financial table with columns like year, revenue, and expenses. A naive parser might read this as a continuous string, making it impossible for the LLM to interpret. A layout-aware parser, however, converts it into a structured Markdown table, preserving the integrity of rows and columns and enabling accurate data extraction and reasoning. Self-RAG is an advanced architecture where the LLM outputs explicit self-reflection tokens during text generation. These tokens, such as retrieve or isRel, signal the system to dynamically query a database, judge context relevance, or check for factual contradictions. This enables the model to self-monitor and adapt its behavior in real time. For example, as a medical bot generates an explanation and encounters a rare disease name, it outputs a retrieve token. The system pauses, queries a clinical database, injects the new context, and resumes generation with verified facts. This dynamic approach ensures accuracy and up-to-date information in sensitive domains. Corrective RAG or CRAG introduces an external fallback mechanism. Before passing retrieved documents to the generator, a lightweight evaluator grades their relevance. If confidence is low, the pipeline triggers an external web search using APIs like Tavily or Serper to fetch real-time information. This ensures the system always delivers the most current and relevant answers. Imagine a user asks about a breaking news event that happened just minutes ago. If the internal vector database returns no relevant matches, CRAG detects the low confidence, launches a web search, extracts the latest news, and builds an accurate response. This keeps the system responsive and reliable, even for rapidly changing topics. Indirect prompt injection occurs when a malicious instruction is hidden inside a third-party document stored in the vector database. If retrieved, the LLM might execute the harmful command. Protecting against this threat is crucial for maintaining system integrity and user trust. To defend against indirect prompt injection, advanced RAG systems use guardrail models like LlamaGuard. These models inspect retrieved context blocks before they are injected into the prompt, screening for malicious instructions or hidden commands. This proactive filtering step is essential for safe and trustworthy AI deployments. GraphRAG combines vector databases with knowledge graphs, structured networks of entities, and relationships. This approach is preferred when applications need to reason globally across large document collections, such as summarizing themes or discovering hidden connections. It goes beyond the localized retrieval of standard vector RAG. For instance, an intelligence analyst investigating financial fraud patterns can use GraphRAG to traverse entity links across multiple files, mapping out a global network view of a fraud ring. This holistic perspective is impossible with vanilla vector RAG, which only finds isolated text fragments. Building document-level security access control into a RAG pipeline starts during the document ingestion phase. User access control lists are saved as metadata alongside each vector chunk. When a user queries the system, their identity is validated, and a metadata filter ensures they only see documents they're authorized to access. For example, if a low-level employee searches for salary ranges, the vector engine applies a metadata filter so only chunks tagged for general access are returned. Sensitive data, such as executive compensation, is automatically excluded, protecting confidential information from unauthorized users. Auto-retrieval or self-querying is a technique where the LLM acts as a query translator. It inspects the user's prompt, detects implied metadata constraints, and dynamically outputs a structured query object. This includes a clean vector search string and specific Boolean metadata filters, automating complex query construction. If a user asks, "Show me the logistics updates for June 2024 related to Texas," the auto-retrieval agent parses this and generates a structured query with filters for month, year, and state. This prevents manual parsing and ensures that only the most relevant results are returned, streamlining the search process. Context tuning and structural compression are essential for prompt payload management. By pruning unnecessary text, removing boilerplate, and summarizing content, these techniques minimize token bloat and optimize processing speed. This ensures that only the most relevant information is delivered to the LLM, maximizing efficiency. For instance, if a system extracts 3 pages of legal fine print to answer a compliance question, a context compression engine removes standard liability text, shrinking the payload from thousands of tokens to just the core informational content. This not only speeds up processing but also improves answer quality. Latency optimization is critical when scaling production RAG pipelines. Since execution paths are sequential, delays can quickly add up. To reduce latency, run vector and keyword searches in parallel, use asynchronous embedding API calls, deploy high-performance reranking servers, and stream generation tokens to the client in real time. Production chatbot, for example, can parallelize database searches and embedding lookups, cutting user wait times from several seconds to just over a second. Real-time streaming of generation tokens further enhances the interactive experience, making the system feel responsive and engaging. Context window starvation happens when the injected document context, chat history, and system prompts completely fill an LLM's input capacity, leaving no space for the model to generate a response. Calculating token boundaries and setting strict caps for each component is essential to prevent system crashes and ensure reliable operation. For example, an application that forgets to cap chat histories may quickly exhaust the model's context window, causing out-of-token errors. By allocating specific percentages for reference data, chat history, system rules, and output runway, you can maintain a balanced and functional prompt structure. Guardrail layer evaluates both incoming user inputs and outgoing model responses against strict safety and operational parameters. It blocks prompt injections and inappropriate language, and validates outputs for structure, data leaks, and grounding before rendering them to the client. This layer is vital for maintaining trust and compliance in production systems. For instance, if a customer bot generates a response containing internal source code, the output guardrail detects the code block, identifies a potential intellectual property leak, and blocks the response. Instead, it substitutes a standard support message, ensuring that sensitive information never reaches the end user. We've covered a wide range of advanced techniques for building robust RAG systems, from defeating structural limitations and optimizing retrieval to ensuring security and evaluation. By integrating these strategies, you can design pipelines that are accurate, efficient, and safe for real-world deployment. Let's wrap up with some final thoughts and best practices. Master RAG systems always prioritize context management, security, and evaluation. Leverage multi-stage retrieval, reranking, and hybrid search for accuracy. Use guardrails and access controls for safety, and automate evaluation with frameworks like RAG, Triad, and Ragas. With these best practices, you'll be equipped to build next-generation AI solutions that deliver real value.